Hi guys, welcome back. We're going to start our lesson on limits. So this is actually in the end of your book, but it's the first unit that you really cover in a calculus course. And the concept of limits is something that is used to define almost every single calculus concept that you're going to come into contact with. So it's only our first day, so it's a little tricky trying to understand what a limit is, but we will be spending a lot of time on them. So if you have questions, always email me. But remember, this is still just the first day with limits. So we're going to start with basically evaluating the limits using tables, graphs. We're not really going to get to the algebra part of it until next week. So the concept of a limit is trying to figure out what the function is approaching as you're given an x value. Okay, so basically, what's the y value? All right, what does the function equal as x gets closer to a certain number? And if a function's continuous, like this one, x squared minus 1, the concept of limits is really irrelevant because for continuous functions, all you have to do is just replace x with whatever the value is. All right. So in this case, we get that the limit would equal 3. So you might be really asking yourself, why would we use limits? And it tends to become more important for functions that you don't get a value for when you do the direct substitution. All right, or for functions that aren't continuous, or in our case, don't have a domain of all real numbers. All right, so those are the functions that we're going to focus on. But for functions like these, evaluating limits is really easy. All right, because you're just doing the direct substitution, replacing x with your value, getting your y coordinate, and there you go. So let's take a look at a function that's not continuous, all right, or that doesn't have a domain of all reals, like this one. So this is a rational function, all right, numerator and denominator. And we can clearly see that this function does not exist at x equals negative 2. All right, the domain would be all reals not equal to negative 2. And we're trying to find the limit as x goes to negative 2. So we can't just substitute it in. Actually, we would start by substituting it in. If you substituted negative 2 into the top, we'd get 4 plus 10, which is 14 minus 14, which is 0 on top, and negative 2 plus 2, which is 0 on the bottom. And that is something that we call indeterminate. It's not undefined, like we're used to when you have just 0 on the bottom. When you have 0 on the top and on the bottom, we call it indeterminate. So we definitely know the function doesn't exist at negative 2, but that doesn't mean that the limit doesn't exist. So if we have a graphing calculator, I'm going to show you how to construct a table. If you don't have a graphing calculator at home, that's fine. But this is just something that we can do. So you want to graph this function. You want to first put this under y equals. So I kind of skipped that step. But you're going to put this under y equals, putting parentheses around the top and the bottom. And then you're going to set up a table. So to set up your table, you hit second window, because right above that it says table set. And we're going to start our table at negative 2 because that's the value we're trying to find the limit at. And then delta table, I'm going to put it at 0.1. We want it to be small, not too small, but just to see what's happening close to negative 2. So then we're going to go to our table. So you have to hit the second graph button, right where it says table. And we're going to see this, and then you're going to want to scroll up a little bit so that you can see the values that occur around negative 2. So at negative 2, we can see that it says error, which we knew that because negative 2 is not in the domain, right? This function does not exist at negative 2, so it's going to give you error. But we're more interested in what's happening around negative 2. So as we get closer, it looks like from the left and the right-hand side, we're getting closer to negative 9. If you're not sure, okay, how do we know it's not negative 9.01? Then we can change our delta table. So if we go back to our table setup, we can start our table at negative 2, but now we can make our delta table 0.01, smaller, and we could look at smaller increments around negative 2. So now we can definitely see that it looks like from the left and the right-hand side of negative 2, the values of the function are getting closer and closer to negative 9, even though it doesn't equal negative 9 here. All right, the limit would equal negative 9. And that would be our answer. All right. So when you see the same number approaching to the left, and the reason why I say to the left is because these values are less than negative 2, and to the right of negative 2, so when the values are approaching the same thing, that value is what we call the limit. All right, so that's when we use limits, when the function doesn't exist, but the limit still does. And we use them for a lot of functions that aren't always continuous, like this one, like rational functions. All right, so let's look at another one. So here's a rational function that also has a trig function involved. So again, it says to construct the table, and we're going to look at values around 0. So the first thing we want to do is go to y equals, and here I showed you, and set it up. So the top is only a single term, so it doesn't need parentheses, x squared, divided by, now the bottom has two terms, so we have to make sure we put in parentheses. And since there's no secant button on your calculator, you've got to put in the identity 1 over cosine x. The parenthesis is put in here for you when you hit cosine, so you have to shut that parenthesis and then shut the 1 for the denominator. And make sure you're also in radian mode. Everything we do with limits and calculus will always be in radian mode when we have trig functions. So now we're going to set up our table. This time we're starting it at 0 because that's the value that x is approaching in our limit. And I'm making my delta table 0.1. And then I'm going to go to table, so hit second graph. And then scroll up, and we can kind of see, so to the left of 0 and to the right of 0, as we get closer, we don't need to make the intervals any smaller. I can definitely see that these values are getting closer and closer to the value of 2. If you happen to see that from the left and right, you're not approaching the same value, that means that the limit of the function does not exist as x approaches whatever number is there. But here, since we are approaching the same value on both sides, all right, we get the limit is 2. Another type of function that is not always continuous, other than rational functions, are piecewise functions. All right, and piecewise functions can also help us evaluate one-sided limits. Okay, so here's an example of a piecewise function where f of x equals x plus 1 when x is less than 0, and f of x equals 2x plus 1 when x is greater than or equal to 0. So both of these functions are continuous on their own, but there could be a discontinuity at the value where they're meeting, or maybe not meeting. Okay, so that's usually the value that we need to be careful of when we're evaluating limits. And we can also introduce the concept of one-sided limits. Okay, limits themselves are innately two-sided. You have to see what the value of the function is approaching to the left side of the x value and the right-sided value, unless we see this sign here. So this implies that we're doing just a one-sided limit. So this little sign right here, we have this positive sign. This is saying the limit as x approaches 0 from the right. All right, so when you see a little plus sign out here, it means that we're approaching 0 only from the right-hand side. So that means we're getting values like 1, 0.5, 0.4, 0.3, 0.1, 0.01. So we're approaching 0 from the right-hand side of 0. So if you're looking at a number line with 0 being in the middle, the values to the right, all right, are positive decimals. So looking at a piecewise function, that means that we would use the right side of 0 would be here, x greater than 0. So we would use this function and we do our direct substitution, replace x with 0, since that's the value we're doing our limit at, and we end up with 1. Now, if you see a negative sign after the number, that doesn't mean it's in front, that it's negative. It means we're approaching 0 from the left-hand side. So from the left-hand side, that would be values of x that are less than 0. So just because the equal sign is here, this is irrelevant. When you're doing limits, we actually don't care about what's happening at 0. We only care what's happening to the left and right of 0. So this equal sign, if it's here or here, does not make a difference in this problem. So from the left-hand side, we're going to use this function because this is where x is less than 0. Plug in 0 for x, and we get 1. So now, since we evaluated the right-sided limit and the left-sided limit, if we were asked to do the limit just as x goes to 0 of f of x, since the left and the right-sided ones are equal, that would be our answer. If the left-handed limit and the right-sided limit were not equal, we would say the limit does not exist. Another way we can evaluate limits is by looking at the graph. Okay, so the last one was an equation that was piecewise. Here's a graph that would be a piecewise function. All right, because we can see we have a curve on this side and a curve on this side. All right, so here, the limit as x goes to 3 from the left. All right, so this is not limit as x goes to negative 3. This is the limit as x goes to positive 3 from the left-hand side. So if we're looking at a graph, we would see that x equals 3 is here, and the left-hand side is on this side. So we'd follow the curve as we stay to the left side of 3, always to the left. And as we get closer and closer to 3 from the left, the function seems to be getting closer and closer to this value, which is 5. Now, if we were asked to do the limit as x goes to 3 from the right-hand side, so again, we're still letting limit as x goes to 3, but now we're on the right-hand side, so we'd follow this curve. Let the x value get closer and closer to 3 and see what the y value is getting closer and closer to. Not what it equals, but what it gets closer to. And in this case, it would be this value, which is 2. Now, if we were asked to find the limit as x goes to 3, since we already evaluated these two individually, we already have our answer. These two are not equal. Therefore, we put DNE, which is an appropriate abbreviation for does not exist. Okay. If you were looking at this, this is what we call a jump discontinuity. Okay, so some discontinuities are vertical asymptotes. Some of them are just holes. Some of them we have a jump. All right, so we're jumping from one function to the next with a gap in between. Another thing we could answer that doesn't involve limits is we could be asked to find the value for f of 3. And on Monday, when we talk about continuity, we're going to incorporate the function value with the limits. So here, if we're asked for actually the value of f of 3, we'd be looking for the point on the graph when x is 3. So if we follow this, there's no point here, but there is a point here. So f of 3 would actually equal 5. All right, and we'll talk about continuity. Basically, what that means is if this limit and this function value are equal, so if the two-sided limit and the function value are equal, that would imply the function's continuous, which we can definitely tell here by looking at this graph. It's not continuous. We've got a jump discontinuity. So let's take a look at another graph. So here we have a curve, okay, that has a hole here. All right, we have our point down here. So if we're looking at this graph and asked to evaluate the limit as x goes to 0 from the left, all right, of this function. So this is the graph of f of x. As we get closer and closer to 0 from the left-hand side, the function value is getting closer and closer to this value, which is 3. If we were asked to do the limit as x goes to 0 from the right, so we'd be over here. So we're approaching 0. X is getting closer and closer to 0, and the y value is getting closer and closer to 3. And now if we're asked to do the two-sided limit, so when there's no sign after it, it implies that it's two-sided. Since the left and the right-hand sided limit are equal, and they both equal 3, that would be the limit of the function. But then the last thing we could throw in is the function value. So if we wanted to find the function value at 0, we would have to look for the point, which actually occurs down here. And that would be, this should say -4, my bad. So the f of 0 is -4. Which again, when these two values aren't equal, that implies that the function's not continuous. All right, so the function's not continuous at x equals 0, but the limit still exists. All right, that's what limits are used for, to evaluate a function at x where it's not actually continuous. All right, so when we were doing rational functions, we talked about sketching them, and we sketched vertical asymptotes versus holes. And that's why we did it right before this unit, because the holes are going to be important when we're talking about limits. So this function right here, if we factored it, the top would factor into 4 times the quantity x minus 1, and the bottom would factor into x minus 1 times x minus 5. So since the bottom has discontinuities, or since the bottom equals 0 at x equals 1 and x equals 5, those would be the two discontinuities of the graph, all right? Because the domain would be all reals not equal to 1 and 5. But there's a big difference about 1 and 5, because since the factor on the top also has an x minus 1, that ends up canceling out. So if we were asked about limits, we could say the limit as x goes to 5 doesn't exist, because looking at the graph, we see that the graph goes to plus or minus infinity, which is not a number. Even if both sides went to positive infinity, infinity is not an answer. So whenever the graph does that, if you have a vertical asymptote, the limit will not exist. All right. Another way to do it algebraically is if you plugged 5 into this function, if you did direct substitution, on the top, 5 times 4 is 20 minus 4, you'd get 16, but on the bottom, you'd get 0. So when you get a constant over 0, that's when you get the limit doesn't exist. It's the 0 over 0 that gives us some difficulty. All right, but in this case, we would know the limit doesn't exist because we get constant over 0. We'd also know it from the graph because there's a vertical asymptote. Now, the limit as x goes to 1 is equal to -1 because the function approaches the same value from the left and right-hand side of 1. And so as we go from the right-hand side of 1 and the left-hand side of 1, the function's getting closer and closer to -1. Even though it doesn't equal -1, there's still a discontinuity there. The limit actually exists there. Right. If we had plugged 1 back into our original function, we would have gotten 0 over 0, which means that the limit could still exist. Unlike here, when we plugged in 5 and we got 16 over 0, the limit cannot exist. All right. So there's a difference between holes and vertical asymptotes. All right, so here, this is not a jump discontinuity, all right, because the graph is not jumping, all right? It's approaching the same value from the left and right. Right. So let's just kind of recap when limits don't exist. All right. Or actually, let's look at this piecewise function first. So for this function, so here we've got another piecewise function. So the limit as x goes to 2 of f of x. So if we wanted to find, this is a two-sided limit because there's no plus or minus sign. So if we wanted to evaluate the left side of 2, we'd have to be using this top function. Sorry, the left side of -2. Oh, this should say -2. Sorry, another mistake. This should say -2 right here. My bad. All right, so the left-sided limit of -2 would give us 11. The right-sided limit of -2, we plug that in, we'd plug it into this function since this is on the right of 2. And we get 11, which means that the two-sided limit, again, this should say x goes to -2, would be 11. If this was actually x equals +2, if we did do that one, the limit as x goes to +2, this function at x equals +2, so we'd be using this one, is continuous. All right, so we would just plug +2 into this, and we would also get 11. All right, so now we're going to recap. So a limit does not exist at x equals a if any of the following happen. All right, so if after doing direct substitution, replacing x with a, you're left with a constant divided by 0. Okay, we know that to mean undefined, but in terms of limits, it would also mean that the limit does not exist. So this would only happen with functions that are fractions. Right? But if you happen to get this, a constant divided by 0, we would say the limit does not exist. If you were doing a table of values around x equals a, and the y values are not approaching the same number to the left or right of x equals a, then the limit doesn't exist because the left and right side of limits would not be equal. If you were looking at a graph, a limit doesn't exist if it has a vertical asymptote at x equals a, which we saw in one of those last examples. And another thing with a graph is if we're looking at a graph and it has a jump discontinuity at x equals a, the limit would not exist. That would be the same as here, constructing the table. All right. When the table of values have two different values, that's usually a vertical asymptote or a jump discontinuity as well. Okay, so the worksheet will be posted on Classroom. Along with this, you can print it out and add in your answers as well. Most of them are either graphs or direct substitutions or piecewise. But again, if you have any questions while you're working on it, ask. This is the first day working on limits, so I know it's a little tricky, but we will get into the algebra side of it as we move forward. Okay, but for these ones, we're just doing graphs, direct substitution. And if you have a calculator to set up a table, you can do that, but I don't think that's necessary for most of these. All right, guys, have a good weekend, and you will hear back from me on Monday.